Okay, so previously we looked at the algorithms for sound generation using Excel. Now I'm going to go ahead and open up Visual Studio here, and we'll go ahead and implement that and just kind of get a feel for how that first part works. So let's start a new project. And we're going to use a standard Windows Form project for this because we're just kind of getting an outline going here. I am going to be using XNA for the audio. I really like the interface we have for that, for this project. So we're going to go ahead and start a new project. I didn't give it an exciting name. Mine's called Form 1. It's always nice to have a nice informative name. So let's just go ahead and look at our code here real quick. We have our basic setup here. First thing we need to do is add our references to XNA. Now, I'm not using a full XNA project here so that I can do the managed graphics really easy, because we're just looking at doing audio here. So I'm going to add Microsoft Framework there, and let's go ahead and reference that. So in order to generate our standard oscillator, we're going to need to set up some variables first. So we need time variable. That doesn't have to be double, but we'll do frequency here. Let's just go ahead and set these right now, just so I don't forget later. So we got those set, and then we're going to need a couple buffers to work from. So while we're doing our generating our waves, we're just going to work with floating point numbers. We're going to try and stay in the range of 0 or -1 to +1. So let's set up a buffer to work with. So we'll use floats for these. Float, and this is actually a buffer, so we need to have that. So float. Wave. Let's call this wave data. Like this. We'll do. I'm going to start with 7. We can play with this number later. Just do 7 of those, and then that's ultimately going to need to be put into a PZM buffer, or a PCM, excuse me. Now the PCM is a 16-bit interface, but it's broken up into 2 bytes. So there's a low byte and a high byte for each sample. So we're going to use a byte array for those, and so we're going to need 2 samples for each. So that's going to be new byte. We need to double that number, so 1400 samples for that. Okay, so the first thing let's do here is just look at our basic equation for generating a wave. So, oops, I should probably, let's see, have it. This is going to return a float. Let's call this generate wave, and it's going to accept the variable of time. So double. And for this one, we'll just use a basic sine wave, which we talked about earlier. So what we're going to do is just return an equation here. So if I can spell return correctly, turn. So we need math sine. So we talked about earlier the mistake that's often made when you research formulas for generation. They'll give you for a sine wave, they give you sine of time. Oops. Time times frequency times 2 times pi. Now, when you do your final algorithm, you'll still combine some of these things. You won't have 2 times pi. You'll already have a constant calculator for that. Not sure why that's throwing it. Oh, because this is a double. But if you looked at the Excel video, I showed you that doesn't work. So let's take frequency out of there. Just do time times 2 times pi. And we're going to return this float. Non-invocable member math pi cannot be used like a method. Oh, yep. Silly me. I'm playing with Excel where it's a function. Okay. So that's done and said. Now that we have that in place, let's go ahead and create a real quick function that's going to generate these samples, these 70 samples we had here. So let's do another function. Private. And we're not going to return anything on this. We're just going to use that sample there. So we're just going to do this with a basic for loop. So I equals 0. I is less than, we're going to do 700 samples here. And I plus plus. Alright, so we've already predefined time, so time set. Actually, we can't do frequency 0. Let's do a better number here. Let's just start with 1 kilohertz just to start with. So we're just going to generate our first data point. So that would be wave data I equals, and then we're just going to call the function we have here. So generate wave, and we'll just pass time to that. So now we're going to apply the frequency instead of inside the equation. We're going to do it as a property of the time equation here. So I'm going to actually do 2 other constant values up here that'll make life easier. So oops, let's do constant float sample rate, and we're going to set that to 44100, and another constant sample rate, which we'll use that inverse sample rate later to optimize things here. That's just going to be 1 over sample rate. So this inverse sample rate actually represents the amount of time that passes between samples we take. So that's where we're going to apply it here. So time is going to increase by the inverse, how do I spell it? Inverse sample rate. And we're actually going to apply the frequency component right on here. So basically time flows at a rate multiplied by the frequency. The variables make less sense this way, but we get the proper calculation of our wave cycle there. So that's all we need for that. Now we just need to convert that into PCM data. So void convert to PCM. Let's make that a function or a method. And we're going to do the same loop here. For I equals, nope, not if. How about for int I equals 0, I less than, we'll use the same number here. And I'll show you, you'll see that'll become apparent here in just a second why we're doing that. I plus plus. And now what we're going to do is pull these samples out and convert them into 2 bytes. And I don't have a lot of time here, so I'm going to have to break this up and start that in the next section.